Welcome everybody to Algebra 2, Section 10.2, Multiplying and Dividing Rational Expressions. This is actually one of my favorite sections in all of math that I've ever taken or taught. And you might think I'm really weird for that, um, especially once we start trying to, because you might not end up liking it. The reason I love it though is because it focuses so much on factoring, um, and I love factoring in general, as well as it focuses on reducing things. And so you get to cross a bunch of things out. And I really love that satisfying feeling of taking something that starts out pretty bulky and making it really small and simplified. Anyway, let's first start off with defining rational expressions. So rational expressions, well, we already defined, we defined rational functions. So rational expressions just means it doesn't have the equal sign. And I want to note that these are in standard form. It's not a definition, it's just a comment on them. They're in standard form if the numerator and denominator have no common factors. And I'm going to emphasize that last part, no common factors. Now, it says a note you can only cancel out common factors. I don't like that word cancel because I don't think it's mathematically accurate. I like the word divide, so I'm going to change that to divide. You might also say simplify. And what I mean by that, I guess we'll see on number 1 what I mean by that. So steps simplifying rational expressions. The first step is to, like I was saying, factor. And you factor both the numerator, which I'm going to abbreviate, and the denominator, which I'm also going to abbreviate. Then the second step is going to be to vertically divide out, see if I can just redo that U, the common factors. Now, on number 1 here, we have 12 over 40. We're going to say, okay, well, we've done one like this before. Well, this is technically still a rational expression because 12 and 40 are still both polynomials. They just don't have any variables. So it's a rather simple polynomial. So 12 over 40, we say, okay, what goes into both? Well, 4 goes into both because 12 is 4 times 3 and 40 is 4 times 10. And so we can say that we can simplify by 10 or reduce by 10. And so the word I like to say is we divide the top and the bottom by, I kept saying by 10, I'm sorry, by 4. So we can divide the top and bottom by that 4. So we can divide those out. Those become 1 in their place because 4 divided by 4 is 1, and the bottom 4 divided by 4 is also 1. So on the top we have 1 times 3 instead of 4 times 3, giving us 3. On the bottom we have 1 times 10, which is just 10. So we have 3 over 10, which can't be reduced anymore. And so we say, hey, we simplified it. And it's important to note that the only reason we were able to simplify or divide out those 4s is because they were multiplying with another term. In this case, 4 is multiplying with 3 on the top, and 4 is multiplying with 10 on the bottom. I want to note that you cannot simplify if it's not multiplication. And the reason why is because when we say we're simplifying this, we are dividing it. And you can't divide to undo addition. Because we learned before, there's a different thing to undo addition, and that's subtraction. So you can subtract to undo addition, but to divide, that means you're undoing multiplication. And hopefully you thought of that in that little gap I left there. So we have to have multiplication in order to undo the multiplication by dividing. So on number 2 here, this is what I was speaking so heavily about, is we have addition and subtraction here on the top and bottom. So what we cannot, I repeat, cannot do, so don't write this down, is a x squared, boom. Those are ones we're good. X and x, boom. Okay, 4 and 1, it will reduce by 2. 8 can go in both of these twice and 3 times and call this good. That is not how any of that works, unfortunately. Although it might be considered easier, it's not accurate in the slightest. And if you were to plug in actual numbers there, like say let's pretend x is, I don't know, 5, and then compare that to the beginning and the end of how it would turn out, it would turn out completely differently than if you were to just reduce willy-nilly like we were looking there. So what we have to do instead is we have to learn to factor the top and the bottom of this. And we've already actually factored these before, and for the first couple, I'll explain how we factor them. From then on, I'm just going to assume that you know how to factor them. So if you don't, please ask for help or go back to previous lessons when we talked about factoring more in depth. So the top one, there's three terms. I make the puzzle for that, and I put a times c, 1 times 16 at the top, and b at the bottom, -8. We say two numbers that multiply at the top, add to the bottom. That'd be -4 and -4. A is a 1, so we can use our shortcut and do the variable, number, and sign from the side of the puzzle. And the same thing on the other side of the puzzle for the other parenthesis. X minus 4, and these happen to be the same. The bottom, same idea. A times c is 1 times -24. B is 2. Two numbers at work. We have -4, +6. We can use a shortcut again because A is 1. So we have x minus 4 and x plus 6. So now what this did is it created multiplication for us. We have these two things multiplying on the top and these two things multiplying on the bottom. So while we still can't reduce just an x and x and an x and x and call it good, what we can do, the reason we can't do that is because each of those x's are part of subtraction addition. And the 8 are not multiplying with anything. But we can reduce an entire parenthesis because that entire parenthesis is multiplying with the other parenthesis. And you can reduce parentheses that are exactly the same. So x minus 4 and x minus 4. And those both become 1. So now on the top, you have 1 times x minus 4, which is just x minus 4. And at the bottom, you have 1 times x plus 6, which is just x plus 6. And this is as far as you can go. We cannot reduce x and x. We can't reduce 4 and 6 to 2 and 3. We cannot do that because now there's no more multiplication to divide out. That's why I really focus on that term or on that specific wording of dividing, because we're undoing multiplication with it. On to example 3 here. Example 3, once again, we can't just say, oh, I'm going to reduce by 2's and call it good. No, what you have to do, and just cross out x's, that'll work. Okay, no, instead, you have to factor the top. The top has a GCF, a greatest common factor of 4. And we're left with x plus 4. The bottom has another greatest common factor, or GCF, and that is 2x squared minus 16, because 2 is a greatest common factor. Now you might notice, well, these still aren't the same, but we might be able to reduce the 4 and the 2 there, because these are multiplying. But before I do that even, you could do that in a step, but I'm going to do all my reducing in one step on this one. I look at the bottom, and I say there's more I can still factor, so I'm going to rewrite the top. And the reason I know that is because this is two terms, so I look for a difference, subtraction, of two things that are both perfect squares. And x squared is x times x, and 16 is 4 minus 4, or 4 times 4. So I'm going to have that 2 out in front, and I'm going to make two parentheses. The first one's going to be x minus 4, and the second one's x plus 4. Now this is completely factored. And so as I go to look through to reduce, I say, okay, 4 and 2, 4 is multiplying with something and 2 is multiplying with something. Yep, we can reduce them. 2 goes into both, it becomes a 2, that becomes a 1. And then I have an x plus 4 and an x plus 4, that becomes a 1, that becomes a 1. So on the top, I have 2 times 1. On the bottom, I have 1 times x minus 4 times 1. So you just get x minus 4. And that is what that reduces to. Neatly enough, if you were to, for example, just plug in a number, let's say we plug in 2 as x, okay? And we get 4 times 2, which is 8, plus 16, that's 24. The bottom, 2 squared is 4, times 2 is 8, 8 minus 32, that's negative 24. So that would give us 24 over negative 24, that'd end up giving us negative 1. Well, if we plug in x is equal to 2 here, we end up getting the same thing. We'd have 2 on the top over 2 minus 4. That'd be negative 2. And that would also reduce to negative 1. So you notice, hey, if we were to plug in some random x value, that we would end up getting the same thing in our initial problem as we would in our final expression when we reduce. And that's how it should be as long as you reduce accurately by dividing out multiplication. And I didn't pick the number 2 to plug in because I knew it would be negative 1. I actually had no idea what it was going to be. I just picked a random number while I'm making this lesson, because it would work with any number in all of existence. All right, number 4, why don't you go and try this one on your own? It is factored completely, so you just reduce the x's to 1 and 1. And 3 and 5 don't reduce, so you just have 3 over 5. And no matter what you plug in for x, it would have reduced to 3 over 5 anyway. Number 5, I want you to try this one on your own as well. 5 is not factored, so I'm going to go ahead and take the top and look for a GCF. That's always the first thing we look for. So I have x, and then we have x plus 7. And the bottom is just x squared. So on the top, I have an x multiplying with the parenthesis, and on the bottom I have x squared, which means it's x times x. And some of us might benefit from writing that out. If you're someone who would benefit from writing that out as x times x, reducing one of them and leaving the other, feel free to do that. Personally, what I do is I just leave it as x squared, and I just cross out that exponent and say, okay, that's going to be an exponent of 1 now. Because I had 2 of them, we divided 1 out. So we're left with x plus 7 on the top and x to the first on the bottom. Number 6, I want you to try this one on your own. All right, this one's already factored too as well. So we have x plus 3 and x plus 3 both multiplying on the top and bottom. So then we're left with 4 over x minus 5. Call it good. And again, you could always check your work. I didn't have a very good minus sign. We could always check your work by plugging in some number for every x value at the beginning and the end and comparing them, making sure you get the same thing when they reduce. And you would here. All right, I want you to try number 7 on your own. So number 7 here, you do have to factor. The top will factor into x minus 3. Whoa, I'm not sure what happened to my pen there. And x plus 1. The bottom will factor into x minus 3 and x plus 2. Then we say, okay, we have everything factored out as much as we can. We have as much multiplication as possible. Well, x minus 3 and x minus 3 are identical, and so we're left with x plus 1 and x plus 2. We were able to divide out the multiplication. And see, that's what I love about this, is it takes this and turns it into this. And you might be like, Mr. Kossel, that's not much nicer. And like to me, that's, oh, it's so beautiful just because it's so much simpler, because there's so much less going on. Like if you were to plug a number into that second one compared to the original, it'd be way easier to plug something into that. All right, I'm going to try number 8 on your own. And you can just ignore the fact that there's parentheses here, by the way. It doesn't affect it one way or the other. All right, number 8, the top factors into x minus 5 and x plus 3. The bottom factors into x minus 3 and x plus 3. And remember, your parentheses can be in any order at any time. So now x plus 3 and x plus 3 reduce, and you're left with x minus 5 and x minus 3. And when I say reduce, once again, I do mean that they reduced because of dividing the x plus 3s out. So they became 1 and 1. And so we did x minus 5 times 1 and x minus 3 times 1. Number 9, you want to do this one? So we have a GCF again, and the GCF here is 20 on the top, and you're left with 4x plus 2. Sorry, let me try that again. 2x plus 1. And on the bottom, you have a GCF of 10, and you're left with x plus 3. Well, we can notice inside the parentheses, that's not the same at all. But outside the parentheses, 20 and 10 can both reduce by 10 to 2 and 1. So you have 2 times 2x plus 1 over x plus 3. Now you might be saying, Mr. Kossel, there's no more we can reduce here. Do we have to multiply this 2 back in? Okay, and the question is, no, you don't, because it's okay to show that it's all factored out, to show that you looked for anything additional. You could also write it as multiplying that 2 back in and getting 4x plus 2 over x plus 3, and that'd be okay as well. I'm typically going to have my answer like this. This one's also okay. All right, on to the next page. Now we're going to look at multiplying these. Okay, so when you're multiplying rational expressions, so one rational expression times another, so we're multiplying fractions together. Okay, and just like when we multiply fractions, I'm going to actually showcase this on number 1 before filling in the blank. 3 over 4 and 2 over 9. Well, 3 and 4, nothing reduces. 2 and 9, nothing reduces. But diagonally, we can reduce and divide those out. So 2 and 4, 2 goes into both once and twice. 3 and 9, 3 goes into both once and 3 times, or thrice. And we're left with on top, 1 times 1 because you multiply straight across, and the bottom, 2 times 3, 6. And you could get the same answer by multiplying all together and reducing at the end. It just makes it makes you get a lot bigger numbers, not necessarily on this problem, but on later problems, especially the ones we're going to do today. And it ends up being harder to reduce later. So what you do is you simplify each fraction. So we're going to simplify the fractions like we did before, as far as what you can reduce, and factor everything out. Then you simplify diagonally, just like we did there. So on number 2 here, we say, okay, well, there's nothing to factor on this one. There's no addition, subtraction. It's all already multiplication. Individually in the fraction, nothing there. In this fraction, oh yeah, we could take care of these x's, okay? And if you want, you can take care of the x's and say x squared becomes x to the first, and x just becomes a 1, okay? And then now diagonally, you can say, okay, well, we still have an x squared and an x. You have a 3 and you have a 6. Now, we can't reduce anything more because 2 and 5 and this 2 and 5 don't reduce, and there's an x here and nothing else on the bottom. So now we keep an account of everything we have left, which is 2 times x to the first times 2. Oh, and times 1, I suppose, which would just give us 4x. And on the bottom, you say 1 times 5 times 1 is 5. So you have 4x over 5. And if you multiply this all together to begin with, you would have gotten 12x to the third over 15x squared, which you'd say, okay, the top and the bottom reduced by 4, or by 3, my bad. So you get 4 over 5, and x squared goes into both, so you're left with an x on the top, which is the same thing. Now, if you're wondering additionally, hey, Mr. Kossel, if I had seen this problem, and instead of reducing vertically like this with those x's, could I have done this diagonally and said x squared and x squared off the bat? 100% you could. Because as you notice, you still just have one x left on the top with none on the bottom, which is what we get in our final answer. So that's perfectly okay. So if you want to do diagonally before you simplify vertically, because it might make more sense to you, go ahead. I would actually personally do that on this problem. I just wanted to showcase to you both ways. All right, number 3 here. Okay, so now we're going to have to factor the first fraction and the second now fraction. So the first one, the top stays the same, the bottom factors into x minus 3 and x plus 3. The second one, we can take a 9 out, and we're left with x plus 3. Oh, and I didn't mean to put a equal sign there. That should be a multiplication over the 1. And we now notice, oh, x plus 3 and x plus 3 reduce to 1 and 1. Nothing else seems to reduce. So just like before, you can have our answer written as 9 times x plus 2 and not distributed in over x minus 3. Or you could also leave your answer as 9x plus 18 distributing in that 9 over x minus 3. And either one's fine by me. Once again, I'm typically going to write my answer like this, just to showcase, hey, I did factor everything out. All right. I'm going to try number 4. Number 4, I'm first going to start off with the 5 and the 15, 1 and 3. And then I'm going to do the 3 and the 27 to 1 and 9. And I'm going to say, wait a second, I can actually do the 9 and 3 again to 3 and 1. So I have all my numbers just giving me a 3 on the top. All right, now I'm going to go through and do my x's. Okay, so I can say, okay, well, I have x to the 5th and x to the 4th. Well, if I take 4 away, it becomes an x to the 1st. And now I can look diagonally and say, hey, x to the 1st and x to the 1st, those just become 1 and 1. So on the top, I see I have an x squared left, and on the bottom, there's no x's. So I'm going to put an x squared there. And now I'm going to turn my attention to y's. So On the top, I have a y to the third and a y to the fourth. So that's to become a 1 and a y to the first, respectively. So now on the top, I have no more y's. On the bottom, I have a y to the first and a y to the first. That would give me y squared because we would add the exponents. Oh, but that is on the bottom. And boom, I simplified. Now, you might have gone through this in a different way. Maybe you started out with a 27 and 15 first, and I started with the 5 and the 15 first. Okay, maybe you started with the x's, and maybe you did the x squared instead of the x to the fifth. Okay, that's also okay. There's so many different ways to go about it that can all lead to the same path. All right, number 5. Okay, this one's going to require a lot more factoring. You have to factor each individual part, so then each numerator and each denominator. Go and try factoring these out. And try this one as much as you can, actually. So the top factors out a 5x, and we're left with 4 minus x. The bottom, you can take an x out, and you're left with x minus 1. On the right, you have the parentheses x minus 1 and x plus 4. And on the bottom, you have x minus 4 and x plus 4. And actually, I'm going to rewrite that top left one, and I'm going to show you why. So I'm going to rewrite this top left one in standard form and put the negative 5x squared first, because this is how we typically write it. We want to write the highest exponent first. And then, knowing that it starts out negative, I'm going to factor out a negative 5x, and be left with x minus 4. And you might already notice why I did that, because it actually matches diagonally with this one down here, and now reduces. Whereas before, it didn't quite match. So that's another reason why I always taught everyone to factor out a negative when it starts out negative, is because I knew it would end up leading to this point to where it'd be helpful for this as well as the rest of the math we were doing. Now I also just look for things to reduce. X plus 4 and x plus 4. X minus 1 and x minus 1. An x and an x. And on the top, you're left with just negative 5. And on the bottom, you're left with 1. So negative 5 it is. So all of this becomes negative 5. And I love that. And you might think I'm the weirdest person ever, but you might have thought that before too. Next, dividing rational expressions. So remember what happens when you divide a fraction, okay? And we're going to use number 6 here to lead into what I'm going to write on the blank. So remember, if you had 2/3 divided by 7/3, what we did instead of dividing by a fraction is we multiplied by the reciprocal. So flip it. Some of us know it says copy, changes to a dot, and flip the second one. Or same, change a sign, and rearrange the third one, okay? There's a bunch of different sayings out there. And now we do the same thing we were just doing on the last page. 3 and 3 reduce, and it's with 2/7, and call it good. And so it's the same as multiplying by the reciprocal, which remember is just a flip version. So 7 here, when it's written as a double-decker fraction, you have this fraction on top of this fraction. I'm going to leave that first fraction the same, and I'm going to change the division to multiplying that second fraction by the reciprocal. So I'm going to flip that one and put x squared minus 11x plus 30 on the top, and x squared minus 6x on the bottom. And now I have multiplication, and now this problem is just like the ones we had on the last page. So go ahead and try this one. So this is going to factor out. Top left doesn't factor, bottom left factors a 2 out. Top right factors into x minus 6 and x minus 5. And the bottom right factors an x out. So now as I look to reduce, I can reduce an x minus 5 and an x minus 5. I forgot the parenthesis there. And those both become just 1 and 1. I can reduce an x, and those become 1 and 1. And I can reduce an x minus 6 and an x minus 6. And on the top, we're left with 7. On the bottom, you're just left with 2. All of that just to get 7/2. Once again, I love that. It's very satisfying to me that all of this becomes that. So once again, our first step was to change it from dividing two fractions, double-decker fractions as they call them, into multiplying by the reciprocal. The first fraction did not change at all. The second fraction just flipped. All right, number 8. Note that this is just the same thing as being over 1. Go and try this one on your own. So the first fraction is going to stay the same. And if you want to go ahead and factor it in that step, feel free. Second fraction just reciprocates. And if you want to go ahead and factor that, feel free to do that as well. If that's too much for you in one step, though, that's okay. Top left factors into 2x minus 3 and 3x plus 5. Bottom left doesn't factor. Top right doesn't factor. Bottom right factors the 3x out. Sorry, just an x out. And you're left with 3x plus 5. And now we look to reduce, aka divide. So we divide multiplication. And I have a 3x plus 5, a 3x plus 5, reduced to 1 and 1. And that's actually all that reduces here. So on the top, you're left with 2x minus 3 and a bunch of 1s. On the bottom, you're left with 4x squared and x, giving you 4x to the third. Because once again, we add the exponents when you multiply x's, or bases in general. All right, I'm going to go ahead and encourage you to try number 9 again, or 9 by yourself too. Just like on the previous one, this is over 1. And now I'm going to go ahead and showcase factoring this out in the same step, but once again, feel free to not do that and just rewrite it in the second step and just flipping the second fraction. So I'm going to factor this out into a 3x minus 2 on the top left and an x plus 5. The bottom staying the same because nothing factors. The top right becoming 1, and the bottom right, 3x squared minus 2x, factoring an x out into 3x minus 2. Very similarly to the last one, 3x minus 2 and 3x minus 2 reduced, but nothing else does. So that's with x plus 5. On the bottom, you have 6x squared and x, giving you 6x cubed. On to our last example of the day. Once again, I would encourage you to try this one on your own. This one, once again, I'm going to change the second fraction to multiplication, or change to multiplication by reciprocating the second fraction, I should say. And there's no factoring this time, so we just look to reduce. We can say, okay, 8 and 2, 1 and 4. And someone might say 4 and 4. No, 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 no. This 4 is not multiplying, it is adding. Cannot do that. Okay, so that's all the numbers we can do. So I'm just going to get a 4 there. Okay, x's. Okay, x squared and x. No, no, no. Once again, that's addition there. So there's no x's we can reduce actually because there's no other x's on the bottom, and so no x's are multiplying with anything on the bottom. So you have x squared and x on the top, just giving us x cubed. And then y to the fifth and y to the fifth. Oh, those are both multiplying with things, 1 and 1. So on the bottom, you're left with x plus 4. And that'd be our answer. All right, that is it today for Algebra 2, Section 10.2.